In this video, I want to continue talking about evaluating limits graphically, or just by using a graph. In this case, though, we're not given the graph, we're given the piecewise function from which we have to make the graph and then to evaluate limits, or in this specific case is to identify values of c for which the limit as x approaches c of f of x exists. So in that sense that we're going to identify intervals on which the limits exist. Problems 29 and 30 are similar to problems 27 and 28. But we have to graph the graphs ourselves first. So what we have here is the piecewise function where f of x is x squared whenever x is less than or equal to 2. So what you might want to do at that place is start at the ending point, which is x equals 2, and to see what that graph would be. And when x equals 2, f of x, or x squared, would be 4. Now in this case, we know that x squared is going to be just a basic parabola shape. And we want the values. The function will behave this way as if it were x squared for values less than or equal to 2. So we have 2. We can plug in a 1 now. We're moving to the left. So 1 squared is just going to be 1. Plug in 0, we'll get 0. And then we know that this function is going to be symmetric about the y-axis. It's an even function. The negative values of negative 1, negative 2 are going to produce exactly the same y values as their positive counterparts. We probably have room to go one further. When x is negative 3, we're going to get positive 9. And so we can draw a graph through that. And we would get something that looks like this. It's the part of the parabola goes from negative infinity, so we don't want to necessarily stop it at x equals negative 3. It goes from negative infinity all the way up to x equals 2, and it stops there. From that point on, the function is going to look like 8 minus 2x. 8 minus 2x could also be written as negative 2x plus 8. So that's a linear function. How do we graph a linear function? We start at the y-intercept, and then we use the slope to graph the rest of it. So we'd start at y equals 8. And a slope of negative 2 says we go down 2 over 1. Now for the next point, which would be 2 comma 4, that point is already there. So we'll skip that and go down 2 over 1 again. And one more time. Now before I draw this graph in this piecewise function, that graph should only run between x equals 2 and x equals 4. So it's just going to be the part of the graph that runs here. Now it doesn't include the value at x equals 2. If we plugged in x equals 2 into that 8 minus 2x, we'd get 4, which is already a point on our graph. So I can erase, and so the second branch of this piecewise function will look like that. It goes from x equals 2 to x equals 4, but actually it doesn't include the value at x equals 4, so that should be an open circle there. So I make that change and leave that as an open circle. Now from x equals 4 and onward, the graph should just look like y equals 4, which is just a horizontal line. And so we draw that in. And that's what this graph, or what the graph of this piecewise function should look like. It has that piece of the parabola, then it has a straight line piece, a linear function, which is sort of diagonal there, sloping down. Then we have this line that has a slope of 0 from x equals 4 and onward. So at this point we're ready to make our analysis of where the limits exist and where they don't here. Again, we can see that there's only one place where we'll have a problem, and that would be at x equals 4. We have differing behavior from the left and the right. Aside from that, the limits exist at every other point. So we would write that the limits exist for, or from negative infinity to 4, and then from 4 to positive infinity. And so that should do it for this particular problem. And we'll go on in the next video to look at number 30, since that's a trig function. That's a little bit more complicated to graph, but we'll take a look at that in another video.